Okay, the first topic we have for this semester is we will start with chapter 12. What is chapter 12 about? Chapter 12 is about factors and the geometry of space. And the first thing we will learn from this chapter is on a three-dimensional coordinate system. Now, how do we construct, by convention, three-dimensional coordinate system? We do coordinate system this way. So suppose we have this x and y axis. As usual, x is the horizontal axis and the y is the vertical axis. Then the z axis will be coming to us. The z axis will be coming to us. Z axis coming to us out from the paper, from that xy plane. Okay, we can say that suppose we have, I wonder if I have that here. Do I have that here? Maybe like this, maybe like this. Okay, so let's say we have this here, and then if this is my x-axis, this is the y-axis, right? Then the z-axis will come up. It follows what they call the right-hand rule. So if you start from, if you do move counterclockwise from x to y, counterclockwise, then the z-axis will be coming out to us. Okay. Now, if we see that this is our xy plane, if this is our xy plane, notice that the x goes to y in that direction, then the z-axis will jump out from that. Now notice that it follows our right-hand rule. Take a look on your right hand. Take a look on your right hand, and the way your index finger moving, right, tells us where the z-axis going through the thumb. So if this is my index finger, right, moving in that direction, then my thumb will be going up. Okay. Can you hear me, by the way? I see my microphone is on here.
Yeah, I can hear you.
Okay,
I can hear you.
Yeah, thank you. Yeah, so now, so that's about the convention about that three-dimensional coordinate system. If I kind of like steal from our textbook, let me still do some screenshot. Give me a second. Then this is what they say. Yeah, you see the second figure, they say about the right-hand rule, right? Okay. Now, our textbook also have some terminologies, which I like, therefore I use it. Something they call right wall, left wall thingy. So let me take the picture again. Hold on. That's the nice thing about doing this on Canvas. Then I can take the picture and then just post it here. It's so nice for me, you know. Okay, take a look on figure number 3. notice that XY plane is what we call the floor, right? Take a look on figure number 3. Okay, now the XZ plane, we call that the left wall. The YZ plane is the right wall. Of course, in my class, I still call them the formal name YZ plane, XZ plane, XY plane, right? But if you try to imagine that with your room, you can call that your left wall, right wall, and then the floor. Okay? Now, next, about coordinates. Coordinates. Coordinates on XY plane must have something, the Z component is 0. Okay, take a look. Suppose I have this coordinate here on the XY plane. Okay, you see then the X has some value, the Y has some value, but the Z has value 0. Okay? If you have coordinates on XZ plane, then what is 0? A coordinate on XZ plane must have the Y equals to 0. Okay, coordinates on YZ plane must have the X component equals to 0. I wonder if you realize this. Okay, let's look back to our two-dimensional system. Our two-dimensional system. If you have a coordinate on the x-axis, what is 0? Then the y component must be 0, right? Does it make sense for you? If you have a coordinate on the y-axis, then the x component must be 0. Now, likewise here, if you have a component on xy plane, the z component is 0. Okay, so for xy plane, the z component is 0. I hope you can relate that now. Now, how about if we have coordinates on the x-axis? Coordinates on x-axis. Try to picture that. Let's say we have a coordinate here, right at the x-axis. Then the coordinate must be some number, comma, the y is 0, the x is 0. Right? Does it make sense? Coordinate on the y-axis means the x is 0, the y is unknown, the z must be 0. Likewise, any coordinate on z-axis must have the x and the y component to be 0. Okay, now please do not underestimate this statement though, because when I have an equation, let's say for example, a little example, find the z-intercept of the graph of, let's say, 3x plus 4y plus 6z equals 12. How to find the z-intercept? Well, we know z-intercept means it is on z-axis. Now, because it is on z-axis, then x and y must be 0, right? Okay, therefore 3 times 0 plus 4 times 0 plus 6z equals to 12. We get z equals to 2. Sorry, 2, not 12. So the c-intercept is 0, 0, 2. Okay? Now sometimes we read too fast without understanding what we are reading. And if you are reading too fast without comprehension and you don't understand those basic terminologies, you lose a lot. I mean, it's so basic that you know it, but it's not in your subconscious. You know, it's not in your subconscious. Like, you still need to think, what is the intercept? Without realizing, yes, the intercept means the x and the y has to be 0. Okay, now how about if we have a coordinate not on the planes, not on the axis? Let's see example 2. For example, we want to sketch coordinate P, which is coordinate 3, 2, 4. How do we do that? In 3 dimensions. Now this one you need to learn how to graph. Okay, now I will not use the graphing method, the tools I have from this computer, but I try to do it as if I need to do it on paper. So please follow me. So we start, of course, with the y-axis. Sorry, this is not what I want. Okay, that's the vertical, and then the x-axis is here. The y-axis is here. Okay, these are right angle, right angle, right angle. Is it right? Okay, this is the x-axis, the y-axis, z-axis. Are you following me in graphing? Please do. Okay, please do. Since you already attend my class, I think you rather just follow me instead of just sitting there like you are watching movie. No, watching movie will not determine your future, but my lecture may very well determine your future. Okay, now then how do I sketch that 3, 2, 4? Now, we usually start from the XY plane first because that's what we get used to. But imagine you see this XY plane not from the usual point of view. It's 3 units in the X direction. So let me make it like this. This is 3 units in the X direction, 2 units in the Y direction. So imagine if from this 3 on the x-axis, I draw a segment parallel to the y-axis, and then from this 2, 0, 2, 0, this coordinate, I draw a segment parallel to the x-axis. So notice that this is coordinate 3, 0, 0. This is coordinate 0, 2, 0. So what is this coordinate here? This is coordinate 3, 2, 0. Okay. Now then, how do we show 4 units up? Imagine on the y-axis you'd go 4 units. Unfortunately, I cannot make it to scale anymore. Okay, so let's say that's what it looks like. Okay, so from here it will go 1, 2, 3, 4. So this is the coordinate 3, 2, 4. Now, if you want to make it look even better, you take this part here, draw parallel to the y-axis, and then parallel to the z-axis. And then from here, you draw parallel to the x-axis. Now, the hard part in teaching Calculus 3 is how the instructor should depict or sketch the graph in 3 dimensions on 2-dimensional plane. You know that's almost mission impossible, right? Now, compare this way of drawing to this one here. Let me borrow this guy, and then, oh, you know what? 3 units in the X position, 2 units in the Y position, and then 4 units in the Z position. You just draw it like this. Now, you can draw it like this and nobody understand what you're doing. Okay? In fact, you can do it this way and still not clear. Until you start making this kind of shadow, this kind of dashes. Then people start, like these dashes here, actually give your eyes and therefore your brain a better understanding about this part here. This is actually standing in the middle of XY plane. Okay? See, if I don't use those dashes to help, it is not clear about this position here. Like when I mark it here, you don't know what is that. You see what I mean? Okay, so doing the quote-unquote the box thingy helps us to understand better about the position in 3 dimension while we draw it in 2-dimensional system. Okay, so try to do this. I can tell you this, my experience though, when I took this class, this course here, Calculus 3 in my undergrad, I did my undergraduate in Indonesia. And Calculus 3 is the 3rd semester calculus, the 3rd semester course. And that was in the fall, the 2nd year fall semester. Now, at that time, we were required to stay 1 month in the summer just to learn to sketch the graph, to learn to graph something. And I remember one of the first things my professor told us to do is to graph a trash can. Okay, and is this a trash can? If I tell you first trash can, and then you see this, you may say, yeah, that's what a trash can look like. But if I don't tell you trash can, I just draw you this, what do you have in your mind? Now you may say, oh, that's a cube, right? Somebody may say, oh, Thomas, that's a square stick together with 2 parallelograms. In other words, nobody will know that's actually trash can until I say that's trash can. Now, my professor's case, he said that, can you sketch something? And I don't need to tell you you don't need to tell me what's that. I can tell you what you were drawing, you know? So, instead of drawing a trash can like this, I think the better one, you know, the blue trash can that we usually have in our classroom? The one looks like this, is rounded. Okay, and then it's kind of like have this part here. And the base is a bit smaller, right? And it's rounded here too. Now, to make it even feel better that it is a 3-dimensional object, we use dashes to help the view. You see? Now, it feels better, right? Instead of the cube that you saw earlier. I mean, you can call that trash can, and everybody says, yeah, you call it trash can, I call that cube, right? This one, it's more like a trash can, even though somebody may say, no, it looks like basket, Thomas. It looks like my laundry basket, right? But at least it gives us the feeling that, well, this is a 3-dimensional object. The top is slightly greater than the bottom. The top and the bottom seems to be a rectangular view with the edges and the corner kind of rounded, right? So those are the important characteristics we try to depict from our sketch. Now, This class is not a class for you to sketch. This is not an art class, so that is not the point. But usually, by us learning to sketch the graph, sketch the solids, sketch the situation, we will be able to see details that we happen to omit if we did not sketch that. Okay, so please learn to sketch your situation. Now, if you happen to know students in biology, students in, especially if they are going to medical field, okay, things that they always get in their class is to sketch. They need to sketch the heart, they need to graph the muscle, the neuron, so on and so forth, like the heart, right? You don't draw heart like this. I mean, yeah, that's our heart for Valentine's Day, right? But our heart doesn't look like that too. Okay, now it has two, actually 4 parts, right? And then your professor will want you to give them name, but you will see that your professor is not really looking at the shape mainly, but the details of the region, the details of the points of what you graph, you know. In other words, it's not about the heart only, it's about the details of that heart. Do you realize what are those, you know? Okay, so learn how to sketch this. Would you like to do one more? Maybe when we deal with negative number, let's see example 2b, maybe example 2b, sketch coordinate. So let me name this coordinate p. Hold on, this is coordinate p here. So sketch coordinate q. Let's say 2, -3, +1. So 2 units in the x direction, and then -3 in the y direction, and 1 in the z direction. 2 units in the x direction, okay, and then -3 in the y direction. Oh, this one is hard. Hold on. Let me use this. I want to drag this longer. Yeah. Okay, this is the y-axis and this is the z-axis. Right now, then -3 in the y direction. So I go backward there. Let's draw this first. Okay, and then from there we go up 1 unit. Parallel to the z-axis, 1 unit. Okay, so this is coordinate q. To make it even clearer, I will draw this. Okay, so if you see this picture, you see, oh, the x component is 2, the y component is -3, the z component is 1. Okay, now the dashes help us to see the reference in regards of the x and the y and the z axis. Next, let's move on. Distance formula. Distance. In two dimension, the distance between 2 points is given by the distance d here. Let's call this p and this is q. we want to find the distance d. Let's say the p is x1, y1, and then the q is x2, y2. Now the d is basically the Pythagorean application to the x difference, the difference in x and the difference in y, right? Okay, so the distance formula d for d squared is equals to the difference of x's being squared plus the difference of y's being squared is equal to d squared. Now, what happened in 3 dimension? This is in 2 dimension. In 3D, we're looking at a box. Basically, we look at the box. Okay, let's draw that box. So suppose I have a box. And let's say the distance we are looking for is the distance from one corner to the opposite corner. Let's find this distance here. Now, the way we do it is by first finding this guy. Okay, notice that we have a right triangle here. Right? Notice that? Okay, so you will see our d squared equals to, let's call this z here, and this is c, that's c squared plus z squared. Can you see? Let me catch that right triangle. This right triangle here. In this right triangle here, it gives us this. Right? Now, but what is c squared? That c squared is a right triangle from here. The right triangle on the ground. Suppose this is A and this is B, then C squared equals to A squared plus B squared. Substitute that in. Then we end up with D squared equals to, actually I don't like this. Let me change that AB into X and Y, sorry. Let me change this to X and Y. So D squared is C squared, which is X squared plus Y squared, plus C squared. As you can see, distance formula in 3 dimension is basically the application of Pythagorean theorem twice. Okay? So, distance between P and Q for P, x1, y1, c1, and Q, x2, y2, z2 is given by x2 minus x1 squared plus y2 minus y1 squared plus c2 minus c1 squared. Okay, now what we learn in algebra for distance formula, we have this, right? Now we extend it into 3 dimension, we get this. Okay, so if we know 2 coordinates in 3-dimensional space, then the distance is given by this formula. Now, corollary, the direct conclusion of that formula, any coordinates, actually I think I should say all coordinates x, y, z with distance r from coordinate P, which I call x1, y1, z1, satisfies x minus x1 squared plus y minus y1 squared plus c minus c1 squared equals to r squared. In 2 dimension, we have this formula in 2 dimension. That's the equation of a circle, right? Okay, that's the equation of a circle. Now, this new formula that we have here, is the equation of a sphere. Okay, notice the extension, right? Notice the extension. Equation of a circle, we have this guy on the left hand side on one side of the equal sign and this guy on one side of the other side of equal sign. Now in 3 dimension, we basically add the 3rd dimension to the 2 dimension we already had earlier. Okay. Let's do a little example. We'll call this example 3 a sphere with radius 5, centered at 6, -7, 3, has equation. What is the equation? Now, I don't know if you pay attention or not. I really hope you do. And if you have any question, any concern, you speak up right away instead of just like. Now, I hope that explains why I don't need you to be here too. If you're not paying attention, I don't need you to be here. Okay. And I mean, hey, you know what is best for you. Even though I know what you should do, but as an adult, you know what is best for you. Okay. If you choose not to pay attention, and therefore you don't have any question, if any arise, don't push it to be my problem later on. Okay? I don't mind you to ask me that again in the during my office hour though, but it's just like, if you need to know it, why don't you just know it now? Okay, well, anyway, so this will be x minus 6 squared plus y plus 7 squared plus c minus 3 squared equals to 5 squared, or simply 25. Okay, now if we want to go on, for example, the intersection of this sphere with xy plane. Once it gets to 3 dimension, it's so hard for me to graph it. I mean, it's so hard for you to graph it too. Not only me though. It's hard for people to graph 3-dimensional object on 2-dimensional plane. Okay, we are losing 1 dimension, right? Okay, but when now we talk about what is the intersection, then we start having some issue in communicating unless we know how to do it mathematically. Can you see the intersection? I don't, but knowing that it is on xy plane, it means the c has to be 0, right? If the c equals to 0, then I plug that in, x minus 6 squared plus y plus 7 squared plus 0 minus 3 squared equals to 25. That's x minus 6 squared plus y plus 7 squared equals to, is plus 9 and then equals to 25, that's equals to 16. So on xy plane, the intersection is still a circle with radius 4. Okay, so if we try to imagine that, let me draw it here. Yeah, here. If we try to imagine that, the circle, the sphere is actually on this side here, approximately like this. This is the center with radius 5. So because the distance of this center to xy plane only 3 units, then, and the radius is larger, so the sphere definitely intersect xy plane. Now, how to depict this is not just a circle, but it is a sphere in space. So I try to draw it this way. You see that these dashes actually parallel to the x and y and z axis. Okay, and then do the further dashes like this. You know, okay, now then when this red sphere intersect the xy plane, we will get a circle centered at 6, negative 7, 0. So you see this coordinate here is 6, negative 7, 3. Okay, now when you project that center to the ground, to the xy plane, you will see 6, negative 7, 0. Okay, and the intersection will be a circle with radius 4. Can you imagine that? It's kind of hard to imagine, huh? Yeah, it's hard to imagine. Okay. At some point, we have to give up on our graph and say, Thomas, if I see it, I know it. Yeah, the thing is, what happens if you don't see it? And we only rely on our algebra, our math. Okay? And don't blame me at that time saying that, Thomas, you cannot graph it. You know, no one can graph three-dimensional, solid three-dimensional things on two-dimensional plane. Okay, we can try, but nothing is perfect. Okay, yeah. Like if you see this picture, the one I just graphed, tomorrow you will not understand that until you follow me in graphing. Then you will see the details. Okay. So this guy here, let me mark it using what color? Maybe I choose this color here, the rainbow one. This guy here is actually here. Okay. Actually, furthermore, we can do something else. So we have that first question earlier about what is the equation, okay, and then the second part is what is the intersection. We can talk about something else, like for example, what is the projection of the sphere onto xy plane. Think about it, like if we see that from sideways, right? Let's say you have this sphere here, okay, and x-axis is coming out from this point, y-axis is here, z-axis is here. This is our sphere. If we project this sphere on xy plane, then what it should look like. Okay, imagine what we meant by projection is this. What we meant by projection is, imagine if you turn on a flashlight from the top and from the bottom of this sphere. Okay, what will the shadow of this sphere look like? Of course, it's what we see here seems like it is just a line, but no, it's not a line. Okay, it is not a line. If we see it from this point of view, we will see a line. But if we have, for example, this is x-axis, this is y-axis, and the z-axis is coming to us, the sphere actually looks like this, right? Now the projection to the ground will actually becomes not a circle. A circle refers to only those coordinates equal distance from the center. No, it is not a circle. We call this a disk. A disk is all the coordinates with distance at most, in this case, 5 units from the center. So the center is 6, -7, 0, right? Now the radius will be 5. Okay, now then what is the equation? The equation will be x minus 6 squared plus y plus 7 squared less than equals to 25. But it has to be on the xy plane, right? For z equals to 0. Okay, actually this one also for z equals to 0 because it is on xy plane. Okay, let me clarify one thing. Okay, a circle, just the boundary. A disk is not only the boundary, but including the interior points. Okay, a sphere is just the skin of a ball. A ball is a sphere with all the interior. With all the interior. Okay, that's some little definition. So when you say sphere, it's just the skin. When you say circle, it's just the perimeter. Okay, when we say disk, is the circle with the interior points. Okay, now let's go on a little bit more. I go on from here, maybe part D. How about the distance of the sphere from the origin? Distance of the sphere to the origin. Okay, when we look at this sphere here, the one in red, right? The sphere in red. How far is this sphere from the origin? Now, notice I didn't say the distance of the center to the origin. The distance of the center to the origin, the center of this sphere to the origin is this length here. The one I marked in purple highlight. No, that's not the one. No, that's not the one. Okay? When we say the distance of an object to a certain point, in this case to the origin, it refers to the closest distance from that object to origin. It refers to this part here. You see what I mean? So how do we compute that? Do we need to find this point first, Thomas? Yes or no? Actually, not really. What we can do is, in this case, happen to be easy. What we can do is we find the distance from the origin to the center of the sphere and then subtract by 5. Right? If this is the one we want, the one I highlight in blue, that's basically the distance from the origin to the center of the sphere. This is the 5. Right? This is 5. Okay, let's compute what is the length in purple. Subtract by 5, it will give us the length in blue. Okay, so let's see. The distance from the center P to origin is 6 minus 0 squared plus -7 minus 0 squared plus, I think it's 3, huh? What is the center again? Yes, 6 -7, 3. So 3 minus 0 squared equals to 36 plus 49 plus 9. Oh, what's that? 45 plus 49 is 94. Okay, so the distance from the sphere to origin is equals to square root of 94 minus 5. I think I need to explain a little bit more why we do that. Imagine on the map, let's say this is the city of Los Angeles, and we are here at West LA College, right? When we say the distance of West LA College to Los Angeles, which distance are we actually referring to? We actually refer to the closest distance, this one. Not the center of LA. No, not this one. It's like the closest distance. I hope it makes sense right now. Okay, what we did earlier, because it is a sphere, so that the distance from the center to any point on that sphere are the same distance, 5. So if I know the distance from this point to the center subtracted by 5, I will get the distance from the origin to the skin. Okay, so when you drive on freeway and you see, oh, distance to LA is 18 miles, then you know it is not to the downtown LA, but it's to the outskirt, right at the borderline of LA City. That's what it means. Okay. Yeah, so basically, if we look back here, what is the distance from the origin to that sphere? It refers to the one I marked in blue highlight. That's basically the length of the segment from origin to the sphere, the closest point. Okay, now I will stop here. It's 7 o'clock. I don't give you suggested homework yet, but if I do in future, maybe I can do some, later on, maybe on Wednesday, then I start give you suggested homework. But suggested homework, if I say suggested homework, I usually denote that with only S, homework. That's for you to try at home. And ask if any question. Basically, that's for you to practice. Okay. The one that you need to turn in, I will always mention that in our discussion board. If you have any turn-in homework that I want you to turn in, then I will mention that in your in the discussion board here, and you will also see the I posted here. Okay, I will call that quiz. So another way to say it, I think, is for suggested homework, that's not to turn in. Okay, that's for you to practice and update yourself. And for turn-in homework, I will call that a quiz. Okay, now this is for today. What I want you to do between now and then, between now and Wednesday, I would like you to start reading 12.1 and 12.2. Please do. I usually don't ask you to read, honestly, because in my opinion, I think my explanation usually better compared to our textbook. It's not because the textbook is bad. No. Textbook you need to read, okay? And there's no visualization, right? You need to visualize that again. When I do my lecture, I can do my little visualization. Now, the thing is in section 12.2, do I have that open with me right now? Yes. Section 12.2. I'm not done yet with 12.1, by the way. Almost, but not done yet. In 12.2, we have some terminology that I would like you to actually read it. And I believe by you reading, you get a better idea. Okay, they are too easy for me to spend time in class to explain. I will still do it, but I will do it too fast, maybe way too fast later on, and you may kind of lose it. Okay, yeah, so please read 12.2. While it is still easy, still readable, please do. Okay, I believe they are actually quite easy to read. You may not just read up to, let me see, just read up to example 4. I think up to example 4 is good enough. Up to example 4 is good enough. Okay? Yeah, that's for today then. I will stop the recording.